Swayam Prabha. Digital India. Educated India.
So today we'll switch gears and talk about machine learning. And I know machine learning, so obviously this is a hot topic, right? Like additive manufacturing is a hot topic. It still is a hot topic to some degree, but about 15, 20 years ago, it was a big, or a decade ago, certainly, metal additive manufacturing was a very hot topic and still is. But what you have to be always, in my mind, a bit careful. Just because it is hot, it's like everything that shines is not gold, right? So you have to actually keep that in mind before you say, oh, well, that's new. It's good. Anything new, you want to learn about it, that's a good thing. But you have to be extremely mindful not to blindly use something or think that, because it's new and exciting, you can just take it and apply it to any problem, right? So that is the word of caution in general, I would say, for anything, but certainly for these types of techniques, data-driven machine learning techniques. There's a tendency for saying, oh, I have a hammer, I'm going to take and apply it to every nail I can see, even if the hammer is too powerful for that nail or too weak for that nail, right? That is a very general analogy, but that happens quite often. I mean, we all as humans are attracted to the exciting stuff, but then we don't think hard about whether it's truly applicable. Is it necessary? Okay, and I say that because now, having said that, indeed there are reasons for us to focus or use machine learning, which is why people are doing it. There are many applications, right? Whether it's, image generation, image object detection, whether it's driverless vehicles, trying to actually interpret the scene automatically. Those are all applications where, machine vision is one of the most, let's say, mature areas for application of, and has really been instrumental in the development of deep learning methods, right? And so there is clearly a need, and there's really applicability of these computational methods, right? But we have to be careful because we are as engineers, the holy grail is always, can I understand the underlying physics? If I have equation like F equals ma, which is true no matter what, at least in the Newtonian world it is true, right? Then that is the most general type of understanding that applies, right? So we shouldn't forget that that is our goal. Of course, these manufacturing processes are pretty complex, so it's not very easy for us to put in a simple equation form, as you've already seen from many things we have discussed. But so there is room for data-driven methods, which is what we do as humans, actually. All right, so what I'm going to talk about today is stuff that I have been excited about probably since about 2011, okay? When I first had an aha moment, and I'll explain to you why I had an aha moment. I said, oh my goodness, I don't know how to answer some questions. I thought I knew many things, but I realized I didn't know how to answer some very basic questions. And I'll give you examples of those types of questions. And it was part of a project. It was a project, federally funded project. But we didn't have much time to do research. It was a development project. So at the end of it, I realized at the end of that 1-year project, I realized I didn't know how to answer some fundamental questions. So I put it on the side and then waited for a few more years till I was able to get some money, get a student started. And for the last, I'd say about 8 years or so, 7, 8 years, we've been working, right? In kind of addressing some of these questions and problems. And as my title suggests, machine learning in manufacturing is a very broad topic, and we can have other discussion about some of the other application areas. But I'm going to focus on how do you enable intelligent decision making, okay, using data-driven methods. Data-driven methods is a more general way. Machine learning is kind of the new, let's say, terminology. But data-driven methods have been around as long as people have been collecting data. Regression is not new, right? Establishing correlation between some variable y, dependent variable, and some independent variable x has been around as long as people have been, from the early days of statistics, they've been there, right? So we do that, and we also intuitively do this all the time as human beings. We make decisions based on data, right? We are, as humans, making decisions based on data. You are making a decision. Is this person somebody I should talk to or not talk to? Look at the person's behavior, and you observe with your senses. You have some cognitive ability based on your mental model, you judge, and you make a decision. And then you approach the person or you don't approach the person. We do this all the time as human beings. So in manufacturing, there are a lot of decisions we have to take, a lot of them, all the way from designing something, and then that design has to be produced, right? So I'll talk about decision making and the role of data-driven methods in going from designing something to making something. And there are decisions at various levels of abstraction that actually we have to go through, okay? And to me, that interests me. So fundamentally, machine learning methods, in my view, are very useful for where you have to make decisions, you have to do some planning, and that planning requires a model, and it's very difficult for me to actually describe let's say, a physics-based model. If I could do that from basic physics, because physics is generalizable, right? At least it generalizes over a wider range of parameter values than purely data. Data is, you collect data, and any fit you do to that data is only valid over that data, the conditions under which you collected the data. Outside of that, it's highly unreliable, right? So you use a regression model, right? Regression model, if it's a good fit within the range of the data, your prediction uncertainty is low. But outside of it, uncertainty increases dramatically. You cannot extrapolate. You can only interpolate with these types of models, right? So you have to keep that in mind. So this is kind of the outline. I gave a similar talk like this not too long ago. And I'll explain to you what I mean by cyber manufacturing as a service, okay? And then we'll get into some of the kinds of things. Like, how do you describe what is the capability of a manufacturing process? Why do you even need to describe that in some form, in some quantitative form? Essentially, can I model what is the capability of a given process or a given machine? Okay, this is what we focused on quite a bit. And then also the question about today, there are more and more, just like you have software as a service. I'm sure you guys have heard software as a service model where you don't need to buy the software. You can simply rent so much time on that software or in the cloud, right? AWS, all of these people offer you access to their cloud server. They offer you software on that, and you just pay for the amount of time you use it, right? Whether it's storage or whether it's compute power or whether it's applications on that platform. In an analogous fashion, there's also things like, some companies are offering, they won't sell you the equipment, all right? Like I think it is Pratt & Whitney and maybe even Rolls-Royce. Their engines, it is power by the hour, they say, okay? Which is, they'll sell you the aircraft engine, but it's really, they're selling you what the engine can do by the hour. You're paying for that. They own the equipment, they monitor it, they'll maintain it, etc. So that is the analogy of software as a service in the mechanical or electromechanical world, the world we live in as mechanical engineers. There's an equivalent of that even in manufacturing, right? So this is not new. Back in actually around 2000, There were some companies that actually started saying, okay, you know what? I will use the World Wide Web to connect people who want something made with people who can make it. In other words, to democratize manufacturing capability or access to manufacturing capability. If you have a machine shop somewhere, you have it in Coimbatore, you have it in Chennai or some other part of India, right? Northeast India, wherever it is, doesn't matter. If I can serve as a broker, I'll create a website that allows me to basically offer people interested in accessing specialized manufacturing capabilities that these machine shops or manufacturing sites have to offer to people interested in who don't have the equipment to produce them. So this connecting designers with manufacturers is not a new idea. Using the internet, that in a sense, that is to do this on demand. So if I want something made, I design something in my CAD software, I should be able to upload this CAD model to this website, and that website basically tells me, okay, and I tell them this is how much I want to make. I want 100 parts made of this design, and I want it, and you tell me how long it's going to take and how much it's going to cost. This capability actually exists. I'll give you, a couple of sites. There are several others as well, and there are more coming online in Europe and other places. But this is called platform as a service, manufacturing platform as a service, or manufacturing as a service. Okay, so on-demand manufacturing. Think about during COVID, right? We all went through horrible period where we didn't have the ability, at least I know back home for me in the US, we didn't have the ability, we didn't have masks, we couldn't buy masks, everything was being imported, but all the supply chains are gone, shut down. So how are you going to find who can make something when you need it? Now forget about COVID. Let's say you as a manufacturer, you're big manufacturers like automotive, aerospace, these are complex systems. They don't make all the things themselves, right? They make some critical components themselves. They may make the transmission, or they may make something like that, engine, if it's a internal combustion type of a vehicle. The rest they will buy, okay, and source it from suppliers. And automotive supply networks, supply chains are pretty deep. They could be 2, 3, 4 levels deep, right? Or even higher. Aerospace is the same way. The question is, if suddenly your supplier cannot supply some critical part to you or a product to you that you need to assemble into your vehicle, how you quickly find out who can make this? How is it done today? You think about it. The way it's done today is they put out a tender. They may have a supplier, trusted supplier network through over the years they have built, but they still put out a tender. Somebody has to bid. And if I am one of the bidders, I say, I can do it. Here's how much I will charge you, and here's how long it will take, right? I do that. And you say, okay, fine, I accept. And maybe you say something else. Somebody else gives another quotation. And based on that, I pick somebody. Maybe I pick the least cost, okay? Or some optimization between cost and time that it's going to take. I need it by this time, so I'm willing to pay a little bit more money. So this is how it's done. How long does this process take? It takes a long time, right? It may take months before you actually issue a contract. Let's say you issue a contract. Suddenly, I may have actually not been completely honest with my capabilities. And basically, to get the contract, I would have told, I can do this. And maybe I could have done it, but maybe my key machinist, who I'm relying on, leaves the company. So I can no longer deliver on time. This happens all the time. Or my machine goes down, or whatever happens. Then you need to find alternate suppliers very rapidly. If you start the same process again, this process is going to take months. So how do you develop a resilient manufacturing network that allows me to know who has capability to do what? Before I actually say, okay, I trust you can do this because I know. Based on data, I know you can make this, okay? That would be desirable. That doesn't exist today, okay? So that is what I mean by cyber manufacturing as a service. It's just a fancy way of saying it's a manufacturing as a service through the internet. But concept of using the internet to connect designers and manufacturers is not new. You can look it up, okay? All right, so what is the problem that excited me, all right? Before I even, and I talked about this certainly, I kind of said this already. If I'm a designer, I'm designing, or I'm a corporate buyer, I'm buying some suppliers. I need suppliers to produce something for me. The question we ask is, how do we find a suitable manufacturer or supplier for this part, right? I call, use my phone, go do a Google search, whatever, right? Or I send out mails, I put it out on the newspaper or whatever it is. That's the way I do this. And those people respond. And then, what I just described, essentially, right? The problem is, this is limited to a few known suppliers, typically. These are the people I know. What if none of them can do this? How can I find alternate suppliers? This is time consuming, as I already said. People may not have the capability to do what I want them to do, okay? What would be better as an alternate? This is where this manufacturing as a service platform idea comes in. It's a potential solution, right? So let's look at what the idea is. Idea is you have a cyber manufacturing marketplace, right, in the cloud. That's not just a broker, okay? There are brokers already today. Broker is like a middleman, right? You want to buy a house, you go to a realtor, and the realtor is the intermediate between the seller and you, right? And sometimes you feel you're at the mercy of that realtor. What I really envision would be where this is not just a broker. This is an intelligent system that interprets what you want made, automatically helps you modify to make your design more manufacturable based on knowledge of who can do what, and then automatically determines who can do what and gives you options of, here are 3 or 4 people who can do this for you automatically, right? And here's how much it'll cost, et cetera, right? But it has to do this in a privacy-preserving manner, because most people will not share the data with you. They will not tell you, oh, here's my machine, here's what I can do. They won't share the real parts, because contractually also they're sometimes not allowed to share. If you gave me a job, I can't share the details of a job with somebody else, right? So you have to do this in a much more secure manner, privacy-preserving manner, without violating trust that you already have with some customers, right? Now, let's come back to this left-hand side. What is in a design? We're talking about design, mechanical design, right? We're talking of discrete parts, discrete objects, discrete products. Plane is a discrete product. It's made up of many, many, many components and assemblies. But what you have is in a design of an object, let's say, is the shape information, geometry information. You have material information. Here's the material, maybe its properties. And you may have some quality information. Here's the dimensional tolerance, some surface specification. Because as a designer, you design this object to serve a function, and that function requires, some tight tolerances, surface quality, whatever the case may be, right? At the very minimum, these 3 things are there in a design, right? And actually many CAD tools don't let you you'll have to add the GD&T information separately. They're not automatic, but let's assume it's there, right? Obviously it's required. And also number of parts that you want made, all of that quantity is something would be specified to the manufacturer. Now I ask you the simple question. You realize the point that, hey, I need to know who's capable of making what. So let me take that question and try to give you a sense of the difficulty in answering that question. This is my aha moment, okay? So let's now forget about a supplier. Let's say supplier 1. That supplier 1 has a milling machine, the CNC milling machine that you saw the other day in that automated cell with robots, etc. Right? Let's say that is supplier 1. And he or she has one machine like that, or two machines. Now, if I ask you the question, what are all the shapes I can produce on that 3-axis milling machine? Tell me all the shapes you can produce on that 3-axis milling machine. Can you answer that question? How? All the shapes that can be made. How would you answer that question? Or first and foremost, can you answer it? And if you think you can answer it, how can you answer it? And how can you prove to me that it's the entire set of all shapes I can produce? Okay. Just work holding device is enough to answer that question, you think? Okay. Number of tools, shape of tools, work holding device. What else do you need? Axes, kinematics of the machine. Okay. What else? Yeah. So that's in the kinematics. Yeah. At the very minimum, you need this type of information. Okay, let's say I give you all of that. You have all of it. I tell you, here's a set of fixtures, you have a vise, you have this type of fixture, you have 50 tools on that machine in its automatic tool changer, right? I give you that. And what did we say? We tell you, okay, it's a 3-axis milling machine. Here's the range of motion. Here are the maximum speeds, feeds that you can actually, velocities that these machines can execute in each of the axes. Here's the spindle, maximum range of spindle speeds, or the maximum value of spindle speed, or the range of spindle speeds. I give you all of that. Can you take that information and answer the question of all shapes I can produce? Huh? Say that again. Machinist. Okay. The machinist. What do you think the machinist, how do you think the machinist answers this question? Okay. From experience. Okay. Very good. So machinist answers this question based on his or her experience. What is experience? I know, but what is that experience? What is the nature of, what is the type of information that actually makes up his or her experience? Yeah. Very good. Very good. So based on his or her ability in the past experience of what they have been able to do, which means it is based on his or her creative abilities, right? It's like cooking. Okay. It's your creative expertise that allows you to mix the same vegetables and produce something better than what I can make, right? Same way, different machinists have different talent, like that, right? But could I have answered this question? So yes, you're right that traditionally we ask the machinist and the machinist says, oh, here's how, based on my knowledge, I can do this or not do this, right? That capability information, the knowledge of what that machine and process is capable of, is in the head of this machinist. It's in his or her neural network, real neural network, okay? That is where it is. And what is that experience? That experience is data. The data is everything they did before. The shapes they have made before, how they made it, all of that know-how is data. Through their senses, their cognitive abilities, they build these mental models, right? Your one machinist's expertise may not be the same as another machinist's expertise. It depends on some obvious things, some not so obvious things, right? So you already start seeing the complexity. If I had to answer, and we are just talking about shape. We are not even talking about what materials, what properties, what quality, all of these things, right? So what about if I wanted to answer this question theoretically? You guys said fixtures, right? And fundamentally, what does the fixture tell you? I have these fixtures. It tells you something about the size of parts you can hold. It tells you how you can hold it, where you can constrain it, its motion, right? So constraint on motion of that object. It also tells you something about what kind of loads you can apply on that object, right? To clamp it down and keep it from moving. And it also, the kinematics tells you the motions themselves, right? That combined with tool geometry. But think about it, even if I gave you the tool geometry and the kinematics, you would have to enumerate exhaustively for every tool. I mean, think about to produce the shape. What is in the shape? Oh, it says, okay, here's the design. It has a hole, it has a slot, it has this curved surface, it has this tolerance. Is it a one-to-one mapping between the tool, kinematics, and fixture and the shape? No. I don't know how to answer this question from first principles. I realized. That was my aha moment. I said, I don't know how to answer this question from first principles. I can try to model. People have done this, right? Oh, tool approach directions, and essentially try to develop rules, okay? Rules, which machinists also have in their head. But those rules are abstracted from this process of gathering data, building mental models. So they are doing true learning from data, machine learning, if you will. Their machine is their human brain, of course, right? That's what they're doing. So that is my aha moment. So this is why machinists can say, look at the object, and you will do the same. If I gave you an object or a design, you look and say, oh, that's a hole. I think I can use a drilling process to produce it. Here's a slot, I can use this. But usually, as you know, in manufacturing, there's more than one way to produce the same thing, right? So you need more constraints to be able to narrow it down to one or two. And this is what happens in practice. So I went around the bush to try to kind of make you realize that this is as simple as it looks, and we take it for granted. Even the simple question of just shape is not easy to answer from first principles, just through modeling. Which is why till this day, you don't have, if we could have done it, you would have a software tool. Now, there are software tools, but they're based on some classification. The earliest such classification was group technology. way back in the 50s and 60s, the Germans said, okay, you know what, I'll group parts, prismatic parts, rotational parts, into groups based on size, some shape, but it's not exhaustive, right? So, you know, enumeration of all the capabilities of a process or a machine, not just shape, materials, properties you can achieve, quality, is very difficult. I mean, you may have the same process, you may have, two of you may have the same machines, right? But the capability of the two suppliers may be very different. One can produce much tighter tolerances than somebody else. That is the ingenuity of their method of how they go about doing it. Okay? All right. Question? No? Okay. All right. So I thought you raised your hand. That's why I asked. Okay. No, that's fine. You're fine. So hopefully now you understand the challenge of this problem, right? Because without that knowledge of somebody's capability, how do I do the matching? How can I say, oh, this is a design? Who can make it? This is an age-old problem, okay? So let's come back. Anybody who makes anything, they have figured out how to make it. That's their trade secret. That's how they make it. There are some common things that everybody knows, yes, but manufacturer, once they've figured it out, they mass produce, fine. But when you talk of making something brand new, you have to go back to the drawing board. And what do? They look at what they need to make, and it takes a while for them. But what do they leverage? They leverage past experience. And that is called variant planning. Variation of what I did before. I have done something similar. You look at the part and say, oh, this looks similar to something I made before. I know how to make that. It's not exactly the same. I'm going to pull up that plan from before, and I'm going to adapt it, tweak it. So I'll minimize the time it takes for me to get to something, and then I'm going to fine-tune it. This is what it's called, variant planning, and we as humans do this all the time. Most things that are made by companies, manufacturers, will effectively use variant planning. Whether they encode these rules in some database or whatever, but the real knowledge, the rules are limited, okay? It's not exhaustive. It's not like F equals MA that applies to everything, right? That is not there. That's the challenge. Okay. Now, the other point I wanted to make, I lost my train of thought here, but anyway, you get the point here. The difficulty of that is one type of decision, which is what is the process? Oh, that needs to be made. Now, what has been the holy grail? Everybody here, I'm sure, has heard generative AI. Maybe you have gone and used DALL-E or something online and generated images or whatever, right? All kinds of people generate fake images and stuff like that and fake videos today using these generative AI tools, correct? But back in the 80s, people were talking about generative planning in manufacturing. Variant planning is one way, which is how we do things today, even to this day. But what is desirable is generative planning, which is I give you the design, and at the push of a button, you tell me what processes, what machines, what instructions, everything down to sending the CNC code to the machine, and it makes it, or to an additive manufacturing machine. Or if it's a complex object which requires multiple processes, the sequence of our processes, machines, operations, everything. That is the holy grail, and that's called generative planning. Okay? Not a new idea at all. 80s, manufacturing people were talking about this. Today, everybody talks about generative AI because there are some tools that allow us to perhaps learn some of this knowledge, underlying knowledge from data and generate, right? Something that looks similar to something before, as an example, right? Image is where you see much of generative AI. Not just image, but text, large language models, ChatGPT, stuff like that you've used. They're essentially generative type of foundational models. So anyway, I know I spent time kind of trying to lay this high level problem for you. Those are the type of decisions that need to be made. And I want to automate that decision making because you may be an expert machinist in your company. The company loses you, you retire or you go away, it's gone, that knowledge. How do I scale it? Your experience, his experience, her experience, everybody's experience, if I can take and infer from it the true underlying distribution of all shapes, quality, materials that I can produce using a process or on a given machine, then I am building that knowledge. Okay? So how do I replicate what a human being does and scale it? That allows me to make these decisions in an automated way. Okay? That is the objective. That's the challenge. Okay? Whether this model or this type of intelligence resides in the cyberspace in some platform, or whether it is in the four walls of a company, it doesn't matter. The problem is the same, right? Problem's the same. That is the goal. Okay? But we are saying, okay, in the cyberspace, because then it democratizes it and automates it. If I want to find a supplier, I can find, and things of that nature. Okay? Any questions? All right. Feel free to ask me. So I already said this. I won't repeat it. Can we enable efficient search of suppliers with manufacturing capabilities that match the part design? That's a practical question, right? Everybody faces it. Okay. Now, I won't belabor this, but this is really saying what I already said to you. Sorry. I made the point already that, level of, the capability depends on the level of experience of the human. Scalability is limited. You can't scale. Everybody's experience is different. And it's time consuming. How long does it take for an expert machinist to gain that knowledge? 30, 40 years. Sometimes, right? What do we need? We need the kind of manufacturing capabilities. What shapes can be produced? The shape transformation capability, the material transformation capability, the quality transformation capability that it takes to produce the finished part, All right, so then the hypothesis we are making. Again, remember, we are scientists and engineers, so we should always have some basis to hypothesize. Based on this understanding, I hypothesize that if I turn this knob, this will happen. Maybe my hypothesis is wrong, but then you test the hypothesis and you try it and you say, okay, well, the data supports my hypothesis or it doesn't support the hypothesis, right? So we are hypothesizing here that can we leverage data? What type of data? Supplier one made thousands of parts over the last 10 years. They made it somehow. They have that knowledge. Hopefully they saved all the parts. And hopefully they saved all how they made it as well, ideally. But let's forget about how. But they at least have saved all the parts, right? The CAD models are there, if they use CAD models, or they have some database, some way of storing this knowledge of here are all the successfully produced parts. And forget about even trying to enable this cyber manufacturing search, but just think about you are a machine shop and you want to improve your ability to quickly say, can I make this or not within my four walls? Forget about what others want to do. You as the manufacturer, you want to have a leg up over somebody else. You want to be able to quickly answer the question of, can I make this? Says internet connection is unstable. Okay. So if you have saved all this data in a database, then I can argue, the hypothesis is that every successfully produced part on that machine in my shop is a sample drawn from some unknown distribution. Remember, I asked the question first, what are all the shapes I can produce on that machine? So if you think of all the shapes that can be produced on the machine, which I don't know what it is, even the most experienced machinist cannot answer that question. Let's assume that each and every product that was produced successfully is a sample drawn from that unknown distribution, right? If it is a sample drawn from that unknown distribution, then from that data, I should be able to infer the underlying distribution. It may not be the complete thing, but at least it will give me a distribution from which each of these successfully produced parts was sampled from. And as I make more and more successful parts, I keep improving my knowledge of that underlying distribution. Next time a new part comes in, I say, okay, well, this new part, is it similar to does it belong to this distribution? If it does, then I say, okay, well, I can make it, maybe. I'm simplifying it, but you get the idea. That is the idea, all right? That is our hypothesis. So we wanted to test this hypothesis. Can I do this? Using machine learning. This is where machine learning to me is useful, okay? Because humans are doing this, they're learning. The expert machine has been learning through experience, through data, right? All right. So this is what we want to be able to do. Deep learning-based manufacturing capability modeling. Because I don't have any other way to describe it right now, what I can do on a machine or a process. But hopefully I have convinced you that this is what humans are doing. The best experts through experience are doing it. So why shouldn't we be able to emulate them? Because now I have better computational tools. I have algorithms. I have these neural networks that can emulate what the human brain is trying to do, or not trying to do, is doing. Okay. Question is, how well can it emulate? All of that we can test. Correct? All right. Now, let me also say this. So suppose you do have this model. Let's assume I'm able to do this. I build these models. It not only helps me answer the question, who can make this, as we discussed, but think about it. How many of you here have used a solid modeling software? Whatever it is. Solid Edge, SolidWorks, doesn't matter. Okay, you've used. So good, very good. So several of you have. And if you haven't, any CAD tool, Autodesk, it doesn't matter what you use, Fusion 360, or Siemens, NX, or whatever. So when you design something in the software, you say, okay, I'm going to make this. You say, okay, I need to design something that, looks like this. He has these features, dimensions. Okay, and you might say, okay, well, this is a square pocket with, pocket in this object with 90-degree corners, and you specify that. You say, okay. And then if you were to go take it to the machinist and say, oh, there's no way I can make 90-degree, okay, blind square pocket. It's not a through square pocket. I can argue we can make something close to a 90-degree through hole square pocket because I could use iridium or something, right? But even there, it's not zero radius. There is some finite radius. The wire diameter radius is there. But if you do that, you don't know till you actually go to the machinist, or the best designers are those who know something about manufacturing. They will never do that. They will specify some corner radius. But your software doesn't tell you. It lets you make whatever, right? But wouldn't it be nice if the moment you did this 90 degrees, the software, a bot pops up and says, you can't do this. There is no way machines in our shop can make this, right? Better still, it comes and tells, you can't make this, but here is the closest ones you can make. That's even better. So it generates some possible options for you to consider. That is design for manufacturing feedback, let's say, or manufacturing feedback for design, I should say, right? Now, design for DFMA or design for manufacturing or an assembly is not a new topic, but it's all rule-based. But you still don't have these type of tools. Even there are rule-based systems that you can incorporate. In some softwares will allow that. But wouldn't it be nice? This is how it should be. That's the vision, but it doesn't exist today. So now if you have these type of models that I just talked about, manufacturing capability models, I should be able to embed them into my design software environment, and it actually tells a novice designer. If you've never designed anything, you just learned the software, it tells you, hey, it makes you an expert quickly so that you don't iterate, right? This is the idea, right? So that also is not available. So it would be nice if I can do this. I can help both ways. Improve designs to make them manufacturable, figure out how to make it also at the same time. All right, so you're wondering where the heck is machine learning in all of this? So far, yes. Title, which title? Yes. Data-driven means I am using data. Humans, what is the machinist doing? Machinist is looking at data, looking at shapes. That's data. I can represent shape as a data, right? In a CAD file, right? Machinist is looking at feed speeds, looking at tool geometry, looking at fixturing. There's some data. Abstraction. What do you think? You think he or she is storing that somehow? How is he or she storing? No. Well, both. Input and output. Otherwise, the machinist cannot answer this question himself or herself also. They're looking at both. They're looking at the input and figuring out how to produce the output and confirm that the output matches the required input or required requirements, okay? And then that is what they have in their head. So that's data. Data about shape, data about materials, data about quality, data about what tools can do what feed speeds can they use, under what conditions there is no chatter, all of these things. What should happen if chatter happens? What should you do if chatter happens? Machinist figures out, the expert machinist at least, figures out, right? They built these models. They're using data. Also visually through the ears, right? Machinists, how do they detect chatter? They didn't build a chatter stability model. They have a chatter stability model in their head, okay? How did they build that? Because they heard it through their ear, right? They heard it and they saw it and they saw the result, output, the chatter marks on the part. They were told that's not acceptable. So now they have a mental model and they have a sense of what sound corresponds to an undesirable event, such as chatter. So those are all examples. They're all based on data, different types of data. Or in the lingo of machine learning, multimodal data. Images, text, sound, force, everything. In manufacturing, we're dealing with multimodal data all the time. The hottest area of research today is multimodal data, okay? Modeling, right? Okay, so let's at least make some progress. We're on 15 already. Um, but feel free to ask me questions. I think, the point is that the techniques, the machine learning techniques themselves are things that are available. You go to, PyTorch, you can use anything, any of those libraries that are available to do that. But I think the point I'm trying to emphasize here is the problems that it's most amenable to as it relates to manufacturing, design and manufacturing, and what can it do and what can it not do, and what are some of the challenges. If you walk away with that understanding, even if you don't understand the details of which specific machine learning, deep learning method or the architecture that I used, you can read all of that, okay? All right, so I already pointed this out, that the types of questions I want to be able to answer relate to manufacturing capability analysis. Can I manufacture this? What process can make it? Process selection. Forget about machinable volume segment. I'll talk about it. If you've identified the processes, how would you sequence the processes, etc.? Yes.
Sir, actually, I'm asking regarding the data collections.
Yes.
So, if you implement the machine learning, so we need more data.
Yes.
So for this,
But can you answer the question? How much data do you need? Do you know that?
No, I don't know.
Okay, I don't know either. So it depends on the question.
Yes.
Right?
So
for certain things, people say you need lots of data, big data. Do I really need that much data? And how much data do I need? Okay, fair enough. More data I have, the better it is. What data? What should I measure? What should I collect? How much of each should I collect? These are all, there are no general answers to this because you need some domain knowledge. Just because in deep learning or training a large language model or training, these big ChatGPT type of things, they kind of crawled the whole web and took everything and put it in and show that you can do that. But do I need to do that? I mean, you cannot do that for manufacturing. Which manufacturer has the compute power to actually train, I don't know how many billion model parameters there are in that large language model. You're not going to train from scratch. You might actually take and fine tune that model or do something of that sort, right? So I didn't mean to be facetious. I interrupted you because I understand your question that yes, you need more data, but how much data do you need is an open question in my mind. And it depends on what problem am I trying to actually answer or solve.
We think that more data, more accuracy will get. So because
in theory, but you can also overfit.
Yes.
Right? I'm not saying more data is bad. In general, what you say is true. Okay? These data-driven methods, the more data you have, generally it's better, more accuracy. The question though is, you have to be careful about overfitting, but also you have to, there's a point of diminishing returns. Where is that point of diminishing returns? Right? Cost of acquiring data is not cheap, right? And if you're going to do something like supervised learning, which is what the earliest applications are all, or classification problems, which require, pairs of data, that pairs, and they're all labeled data. So some human being saying this is a cat, this is a dog, and in images, and labeling it, extremely laborious, right? I mean, if you had to do that in manufacturing, the kinds of data we are dealing with are time series data, force, vibration. You'd have to sit and label all of them, right? It's not a very practical, if I think about it, it's not a very practical thing. In some circumstances, it may make sense to do labeling. Yes, I do need labels to answer the question of, is my model, which maybe is based on unsupervised learning, which does not require labels, is it correct? For that, I need to know what is correct, right? For that, I need labels. But I would argue that, yes, while in general, more data is better, but I don't know how much data I need for different classes of problems in manufacturing. What is the right amount of data and what is the type of data I need? Both, in my mind, are important questions. And you can't, I think, answer that without some domain knowledge. You see, the machinist knows he or she is not collecting. If it's chatter, they're listening. Maybe also observing with their eyes, right? But they're not collecting everything else with their mind. They have filtered out because they realize there is a cause-effect relationship that they have understood, inferred. So that is the challenge. Okay, to me, I'm not saying more data is not good. Yes, indeed. Even what I said, if you have a database and the more parts you successfully make, you should be able to infer more accurately what the underlying distribution is. That is true. Okay. So anyway, but did I stop you from asking your question?
The thing is, we are, as a research perspective, if you look, we are collect the data from the literature, right? So if supposed to, I decided something like tribological parameter, if you want to collect from the literature, so we need to go more literature survey. So that's Willis survey. That's not given the proper all the data. They given the what the data they actually done the research. So how we get more data, or is there any other way, or we can get it?
That is a challenge across the board in anything you do with machine learning. Okay, so not only how do you get the data, how much data, where can you get it from? Okay, these are all challenges, and the data that even if you scour the internet and look at publications. You can say, I'm going to take all these publications, I'm going to Google Scholar search, find all the papers on turning and roughness, and I'm going to actually use a large language model to fine tune it and ask it to do keyword search and collect all the data, numbers. So if it can read the numbers, do something like that, you can try. But you have to know, they may not all be the same type of parameters everybody measured under the same conditions, same materials, etc. Right? So people have looked, it is a problem. It is indeed a challenge. So that's why curating the data set is very important for you to actually ensure that these models work properly and they give you something meaningful, right? You have to curate them. That's not an easy task. We spent a year for one of our problems to actually curate data. We had to generate it ourselves. If you look at what happened in machine vision, people came together. They were facing these kind of problems. So they came and they created the image data set. I think that ImageNet came out of that. So they all got together as a community and said, we won't be able to advance it till we create. So people in manufacturing have not done that, have come together and said, okay, we have these common problems. We will come together and we will contribute data, that a corpus of data that actually is curated and allows people to use that data to at least develop baseline models, and then they can fine tune on their proprietary data, right? It has not happened. People are talking about it, but it's not happened in manufacturing because always people are concerned. Manufacturing, you're making things to sell somebody and make some profit. You think that by giving up your data, you are losing control over your competitiveness. So that is indeed a challenge, okay? But the other way is to supplement some real data that you may have collected with synthetic data, if you can generate. Much of our early work was synthetic data to test our hypotheses, okay? And I'll give you examples of what kind of data we are talking about, right? Just for research, to be able to answer the question, can I learn and how well can I learn kind of thing, all right? Does that help answer?
Yeah, thank you. Thank you, sir.
All right. Okay, let's move on. Okay, our first effort was just to focus on shape, not even worry about many materials, properties, and quality, etc. We have done all of that too, but I won't focus on that. So we want to be able to do generative modeling of shape transformation capabilities of cutting operations. I'm a machining guy, we're manufacturing, so I'll pick. And the other reason is, if you go back in the literature, the automation of process planning in manufacturing, the earliest efforts were all focused on machining. The most advanced attempts at trying to build generative process planning systems, that is, given a design, how do you produce the part automatically, generate instructions? All that research was focused on machining. It's pretty complicated for machining, actually. So that's where the most mature research has been in the past. But okay, so you were talking about data. So where did we get this data, right? We want to be able to answer the question, can I, without labeling, I don't want to label. Labeling supervised learning is okay for certain types of problems. But in manufacturing, think about it. When you do supervised learning, you're doing what is called discriminant type of models. You're building discriminant type models that can tell you difference between good and bad. You say, okay, I have a good part, I have a bad part, right? I want to be able to learn the boundary between a good part and a bad part. Okay? So how do you identify that boundary? In order to identify the boundary, you need two things. You need something that is a data set for good and a data set for bad parts, right? You need that. Then only you can say which one is good and learn that boundary between the two. You can learn that's the only way to do it. But think about it. In manufacturing, how many people store bad parts or knowledge of bad parts? They only care about good things. In fact, if you go to a manufacturer, it's not that they don't have bad things, bad parts happen, but that is not desirable. So they want to minimize that bad part significantly. So which means that their corpus of data that they may have would be heavily skewed towards good parts, not bad parts. Now you have a totally imbalanced data set. You have very few bad parts that they may or may not even have, and large number of good parts that they made. Now try to learn using machine learning to learn the boundary between the two. When you have imbalanced data sets like that is a problem. Okay? So that's the other reason, while classification type of problems are the easy, low-hanging fruit problems that people classifying good, bad, those type of things, whether it's for inspection, whether it is for whatever type of application in manufacturing, people have been doing this or trying to do it. You'll find a lot of papers in this. In my opinion, people recognize that getting good, bad data is hard. Nobody keeps it. So I argue that it's better for us to look at unsupervised learning, right? Which means plus I don't have to sit and label, this is good, this is bad. I just have to have something that I say, okay, these are all the parts and shapes that I have successfully produced on a lathe. Okay? I produced it because I have made it. That's all I have. Okay? I don't know what I couldn't do because I don't know what the machinist threw away. The machinist may have never told me as a supervisor what he or she could not make, right? So, given that assumption, I want to be able to train a model that learns the underlying distribution, probability distribution of shapes that are embodied in the data set of successfully produced parts on that lathe. So every part I made on that lathe successfully is part of that data set. It has a shape. I have all of those shapes. And I want to be able to learn what is that underlying probability distribution from which these parts came from with these shapes. Okay? If I can do that, then I can use that model to generate typical shapes that this machine can make. That's the idea. Okay? So we generated our synthetic data set. We picked a simple problem, okay, in this case. So here, this is somebody actually did this. There's a group out of Purdue University, and they were doing classification they were using discriminant type of models where they needed good and bad. Okay? Well, I don't know the set of all unmanufacturable features. When I don't even know what is manufacturable, how do I know unmanufacturable features? That's the challenge. So here we took their methodology to create shapes. In this case, that we considered 3 operations: turning, grooving, and chamfering. I can do all 3 on a lathe. Okay? Obviously, these are just for academic exercise. We have only picked 3. These are examples of shapes. I can write a macro in SolidWorks, and I can generate by varying the variables of this geometry, A, B, C for turning and whatever, all of these things, and generate hundreds of parts or thousands of parts. You can run the macro and it'll keep generating, right? That's what we did, or my student did, I should say. Here are some examples, the kinds of CAD features that were generated, right? Synthetic data set in this case. What is ideal would be actual parts. Only manufacturers have those. We don't have them, right? But we are researchers. We are trying to figure out whether I can actually learn this. If I can learn it and show, then I can tell the manufacturer, this is what you do. Apply it to your data set. Use my Python script that'll do this, right? That's the idea. So in this case, we only did about 450 parts. The training data set, 450 training CAD models, right? Usually when you do machine learning, there's either a 60, 40, 70, 30, 80, 20 type of a split that you take, and you take 80% of the data for training, remaining balance 20% for testing or validation and testing. Okay. And what we did was each of these CAD models was voxelized. So we are working in the voxel space because voxel is it is essentially a spatial occupancy enumeration technique. It is basically taking a region of space where in grid-shaped space where you can place this object and you subdivide it equally, right? So it is what you do in finite element analysis, discretization. It's what you do fundamentally. So voxelization, there are algorithms you can actually download open source code for voxelization. Now, of course, there are many different types of geometry representation methods, right? You can use point clouds, you can use meshes, you can use voxels, you can use other types of representation, more complex representations like boundary representation and so forth, right? Inside a CAD model, the way it's storing geometry is using boundary representations, which are really more extensive. And again, I won't get into all of that. If you're not familiar, don't worry about it, but it's inside a CAD model, right? So here we take these objects and we discretize it into voxels. Why? Because these have to be, essentially input into some sort of a network. So I can, in each voxel, if there is any material there, voxel is like a cell, right? It's a grid and a cell. If the object in that grid intersects with the object, that is the grid intersects with the object, there is some material in the cell. So it's 1. If no intersection, 0. So I have ones and zeros, right? Effectively. That's all you do. So anyway, what did we do with this data set, right? We built models, okay? So here it says the generative model we built were 3D VAE GAN. Now, most of these image generation tools that the machine vision people have used are 2D, right? They're basically 2D images on which they train to recognize dogs, cats, car, whatever it is. So these are 3D versions of those, right? It's a 3D VAE GAN. VAE stands for Variational Autoencoder. So these are encoder-decoder type of models. If you have not heard about it, think about it as some way of taking information and encoding it into something more condensed, okay, which people will call a latent vector, some sort of a latent vector representation. Think of it as a vector, right? Long vector of some dimension that is a representation, a condensed representation of information in this geometry. And then decoder is to take that condensed representation and expand it back to its 3D image, okay? Encoder, decoder. Without a decoder, you can't generate. You can't generate the image, right? You can certainly encode it into something very compact, some sort of a vector of 1, zeros, whatever, right? Numbers. And then from there, you have to decode for a generative model. So VAE is a variational autoencoder. What it does is basically it encodes it into a distribution, assuming a Gaussian distribution, like a normal distribution, with a mean and a standard deviation. So it says, okay, all of my objects, all of my 3D objects in my data set, right, are going to be encoded into vectors, okay, of a mean and a standard deviation, or into a vector, basically mean standard deviations. Now I can sample from that distribution if I want to generate. I can take a mean value, I can take a standard deviation and use a decoding network, essentially the transpose of what I had, okay, to encode and generate a three-dimensional image, okay? So conceptually, that's what's happening. What is GAN? GAN, I don't know how many of you here know what GAN is. Anybody? Okay, tell us. What does GAN stand for? So GAN stands for Generative Adversarial Network, okay? Now that, obviously, terminology in machine learning can be quite, it took me some time to understand what it is, but it's fundamentally a game theory problem. It's solving a game theory problem, okay? And what is game theory? Fundamentally, it's doing this. It's saying, okay, I have a data set. This is the real data set. I will train a machine learning network, okay, that learns what this real objects are, okay? I will also train another network, which is called the generator. This is called the discriminator. This is a generator that will learn to generate fakes, okay? It'll try to generate fakes that try to match the real ones, okay? It'll try to generate fake images, okay, in 2D, fake images that try to emulate what the real ones are. And if I keep training, then, and so by minimizing the loss between the real and the generated, I can train the weights of these networks such that I eventually get to a point where my generator generates images that my discriminator cannot tell if it's real or fake. It cannot tell the difference. That means I have now trained a network, the generator, to learn whatever is the real distribution behind that data. Conceptually, that's all it does, okay? So that's called a GAN. And this probably developed in about 2015, 2016, around that time frame. It clearly revolutionized. Now, it has its problems, nevertheless, but this is what attracted me to it, the fact that you can generate the underlying distribution or learn the underlying distribution or try to learn it. In this case, we had to combine both, variational autoencoder and GAN, okay? Yes? Yeah, it is. I mean, in this case, yes, indeed, okay? So the overall architecture I don't have, but you can look at the paper. It actually shows you where the VAE is and where the GAN is. I'm interested in the generator, which is coming from the GAN. So yes, the VAE is being used to encode, right? You can also decode, but in this case, the decoder network is really the generator, okay? The GAN network, okay? That's what is happening. Okay, so forget about the details. There is some machine learning model here called the 3D VAE GAN. You want to know what it all involves, what the architecture is, go look at the paper, okay? Or read up about VAE and GANs and you will understand. I build one for turning based on the turning synthetic data set. I build one for grooving based on the grooving geometries I created. I build one for chamfering. And I can do this for all the operations I care about that I know what are typical chamfering shapes and etc. And I trained it. So this is a voxelized version of one input. This is just showing you one example. If this is the input, what this model learned, the trained model does is it generates an output that is as close as possible to this input, okay? So this is showing you that my 3D VAE GAN model for turning did a pretty good job in this case of reproducing the input, right? Looks very similar, right? This is, I'm showing you in 2D, but it's a 3D. It's just one view of it. And same thing for grooving, same thing for chamfering, okay? Now, if I take some object input which is very different from, let's say, typical turned shape, and I feed it into this trained network, it will produce something which may not look anything like the input shape. What does it tell me if that is the case? That tells me that this input shape I may not be able to produce because What I can produce, I showed you. It's not very similar to what you input. Based on my current knowledge, that's the best I can do. That is the conclusion. So this is like an unsupervised model that has learned from some data that you have of what you have made successfully, of what you can make today, right? And same thing for grooving, chamfering, etc. Yes?
So, like basically, we are using AI for the dimensional detection and GAN for feeding in the vision capabilities into the model.
Yes, well, or rather, think of VAE as being used to encode, right? Generate encoding, and then basically the generator and the GAN network to be able to learn to generate similar things.
Like we are using GAN here for the inputting the vision capabilities into the model.
What the generator is basically it has learned the capabilities of the model. Yes, capabilities of the process in this case. Indeed. Yeah.
So like when you are giving some random input,
Correct.
it is producing something.
Correct.
So it is telling that the random input which you have given
Mhm.
can't be produced, but this is the best one.
Correct.
To be produced
That is right.
with the machine capability.
That is right. And that random input, if it's too far from anything I saw before, okay, then I will obviously produce something that is very far from your input. And if you compare the difference between the two, you'll say, okay, they're not very similar. You can also, I'll show you something about similarity metrics as well. But conceptually, hopefully you understand. You can do this for every operation if you had data, right? So now I have trained these models. I never labeled anything. I mean, I argue this is not labeling. I'm not labeling individual parts. I'm just saying, here is my set of all turned shapes. Here's my set of all grooved shapes, chamfered shapes, right? That's all I did, okay? All right, so how do I use this? This is one way to use it, okay? So what happens in manufacturing? So if I were to, let's say, if I build something like a process capability advisor, something called, I say I build an automated system, okay? In machining, what do? You start with a raw stock. You start with some cylindrical stock if you're only dealing with turned parts or parts produced on a lathe, either for grooving, chamfering, or turning. And you start with that raw stock, and then let's say you groove, then you turn, and then hopefully you produce something that is similar to the query part that you want to produce, right? The input, final shape that you want to produce. Now, given that I have trained models based on past experience that I have, past experience that is embodied in the data of turned parts, grooved parts, and chamfered parts that I used to train these models. So here only two are shown, grooving and turning, right? This 3D VAE GANs. Let's say now I have a new part I want to produce, okay? This part, let's say, has some turned feature, it has some grooved feature. It may also have chamfered feature for that matter. Let's say in this example, it only has grooved and turned features. Now, I take this query part and input it into this model first to see if the grooved feature in my model, in my query design, is producible by this process. Okay? So if it is, because what will this model give? It will give me the closest grooved part. It will not give me everything that is in input part. Same thing for turning. Now, if I take these two and combine the Boolean of it, that is my final combined output. Does everybody understand Boolean operations? Union, intersection, set theory, the basic set theory, but this is set theory applied to geometry, okay? So combined output, right? Now, if this combined output is similar to my query part, then I know that by using these two operations, I can produce that part. That's one way to use these models. Now, it is not telling which process to use first and second. I'm not answering that question. I'm just saying there is a grooved feature there is a turn feature, and I can produce those features, and therefore I can produce this part. That question it can answer, right? So here's some tests of that. So so here are objects. These objects were never seen by any of these three models that I trained, because each model was trained only on either turned parts only, turned shapes, grooved shapes, or chamfered shapes. It never saw combinations, right? So here now, object 1 has some groove. It also has chamfer at the right end. So I put it through the grooved model and it shows me the closest groove shape it can produce based on my past experience. It predicts some groove, certainly, but the rest of the object doesn't look anything, it doesn't have the chamfer. If I pass it through turning and it says, okay, well, this is what I can produce for turning, it still doesn't show me any chamfer, okay? It doesn't. So this is the union of these two, okay? Boolean combination of the output of the grooved model, output of the turn model, it's what it gives me. Same thing here, look at object 2. It is much more accentuated chamfer. You do the same thing. The combined output does not look anything like the input, right? Same thing finally here. So these are all unsuccessful, invalid combination of operations. I can't use them to produce that desired geometry, is the conclusion I draw, okay? Now, it is as of today, because that's the data I had, right? Based on which I trained these models. Now, let's look at a place where it works, okay? So, here, you look here. So, I have this shape, object 3, looks like this. I ran it through my grooving model. I get this. I can produce that groove, it says, right, which looks similar to the groove here. I run it through the chamfering model. It's no longer grooving, turning. See, here I did grooving and turning models. Here I'm doing now grooving and chamfering models. I mean, this is a contrived example. Obviously, we shouldn't be putting it through a turning model in the first place, but I'm just showing you an example. So grooving and chamfering, and indeed it says I can produce that chamfer. I do the Boolean combination and it looks quite similar to the input, saying that these two operations together can produce the desired shape. That's one use of these generative models for generative capability models, if you will. Okay? Any questions? At least you understand the idea. That's important. Yes, indeed. Indeed. That's the holy grail, okay, is to be able to generatively plan everything. All right. Now, here we answered this question of, is this total combined output similar to the input visually by looking at it ourselves with a human in the loop, right? I'm a human in the loop. I look at it and say, yeah, it's similar. Fine, good, right? But wouldn't it be nice if the machine itself automatically compares and says, it's similar or not similar, okay? That is the next step for us. So this is showing you just schematically this architecture. This is an encoder decoder framework. This is the, kind of, in this particular case, actually, we took out the VAE GAN, okay? All this is an autoencoder decoder framework, all right? So this is encoding the real shape into some latent vector, decoding it, right? And then I compare what is decoded, what is learned and generated with some randomly picked object from the data set that wasn't used to train, okay? So you essentially are comparing similar pairs and dissimilar pairs. This object that was produced and the input, these two make up a similar pair. If they are similar, output should be 1. If this and this are dissimilar, and clearly you can see they're dissimilar in this example, output should be 0. Okay? So I have trained such a model. Don't worry about these kind of things. These are all machine learning. There's a reconstruction loss when you train it. This is called a Siamese network. Siamese network is like Siamese cats, right? Twins. I'm trying to recognize twins. In this case, these two are twins. These two are not twins. Okay? That's what the Siamese network does. And it does so by comparing what is called a triplet loss. Okay? So this type of a network allows me to automate this human in the loop activity to say, what I produced as an output, is it similar to the input? And yes, no. Okay? Can be automated. Here's an example of that. Okay? I trained it. Trained such models, again, in this case, we extended it not just for turned parts only. I said late parts, milled parts. Okay, so I built two models, one for lathe, based on typical shapes I can produce on a lathe, which includes turning, grooving, chamfering, and then for mill parts, prismatic parts. Okay, I built these models just like previously, different models. I put in a query part as an input after I have trained it, and it outputs and says, okay, well, yeah, this, if it's similar, I should get a number close to 1. So I get, clearly this is, output is similar to the input, I get something very close to 1. So it says lathe should be able to produce that. Whereas here, if I put this object into this model, which has only seen milled parts before, it produces some random thing which doesn't look anything like the input. So the similarity index is much lower, okay? And therefore, I pick this. This is automating that decision making. Instead of me doing it with my eyes, I'm doing it this way, okay? You can do these kind of things. All right. Okay, again, these things, if you're not familiar with machine learning and interpreting confusion matrices and stuff like that, let's not worry about it, okay? It's not important. This is just showing you that you can do these kind of things. Now, yes. I'm going to sit if you don't mind. My back is hurting, so.
Instead of like training multiple GAN models, is there a experiment which tried out like a multi-model like you do in like
Indeed. Yes. Yes. A combined model, which takes all the parts and all shapes. We did. And we found,
which embeds the capabilities of multiple.
yes, indeed, multiple processes. We did. And unfortunately, that type of a model doesn't perform very well, we found in our work. We found that that combined model does worse than individual models. So, yeah, you can argue that if I have to train one model for everything, but I can argue both ways, right? Yes, it would be nice if I have one combined model that learns the capabilities of all the operations that I perform in my machine shop. But I think that's a very difficult problem for these type of networks to learn. Maybe I need a very large network. I need lots and lots of data. This is where maybe data becomes a...
If we have a like really big model, then each part, segments of the network could be learning different.
Yes, but I think that's a tougher problem, frankly, in my opinion, based on our experience anyway. And we tried it. It didn't work very well, so we didn't do it. It's reported in the paper, by the way. But we think that individual models are fine because, what I want in the end is, if I want to answer the question, what are all the shapes I can make on that machine? I just take the turn model and I can say, here's what I can do with turning. Take the milled model, here's what I can do with milling. Here's what additive manufacturing, here's what I can do in fuse deposition modeling or selective laser melting or whatever it is, right? Yes.
We have like multiple models. Is there something like similarity?
Actually, you have to use the mic because they're recording this. Whoever wants to watch this will not hear your question. Okay? So please use the mic.
Let's say we have multiple models like which we are doing right now. Is there a feedback mechanism, something as such, which we can use to like find the best order of the processes which we can use to generate the model? That is one more thing which we can.
I'm going to talk about next.
Okay.
This question you're asking. Okay. All right. So, indeed. So, if you think of machinable, real parts, all those examples, assume that the entire part turning means the whole part can be made by turning. That's not true in practice. Most parts have features that require other operations, which is where I have to, one way to do that, what does the human mind do? I give you an object which has multiple shapes. It has chamfers, it has this and that, and maybe it's a part that has both turned and milled features in it, right? In reality, I give it to you, what do you do? You quickly, your mind basically, through your vision, identifies that these are turn features, these are milled features or prismatic, some other operation required, right? So it segments that object into different shapes and operations. So This is what, and then once you can identify, then, so I want to be able to identify all of the operations required in a part object, 3D object with multiple features. And then the next question is, okay, then in what sequence should I do this? Okay.
And one more thing is like we have a process few which can do multiple steps, like reduce the number of processes.
Huh. Yes. Well, but that is
Let's say the same feature
understood.
could be
Understood. So yes, and
least
that's
possible time or like least possible energy.
yeah, but it requires more data. It requires other data that we don't have at this point, right? At least not in this problem. We have not considered that. But if you have other data, right, you say, okay, I want to bring in energy consumption. The more constraints you start adding, or data that represent constraints you start adding, then you can further discriminate between them, right? But first we want to be able to even do this. I mean, this is what happens in practice. I want multiple options. Then I say, oh no, you know what, this option won't work. It's more time consuming, more expensive, or this machine I don't have, whatever. So yes, you can do those things, you know, but this is where, if you want to solve the overall process planning problem, there are so many difficult questions that need to be answered. People haven't been able to come up with a system that can answer all of it for a reason, right? So step by step in our case, okay? So, okay, let's talk briefly about semantic segmentation. What does this mean? This is terminology again, and computer scientists have come up with a lot of this terminology. Segmentation is what I described. You take this object, this is a plastic bottle. It has this complex contoured shape. It has some ribs, right? It has a cap. All of these features it has, right? Now, in this example, this whole thing was blow molded. We know it, okay? But if you really want to describe the overall manufacturing process, you also consider, you have to actually produce a mold. But mold has to be machined, etc. All that has to happen. That led to this final product, right? But let's forget about that. Think of something else. So think of an object which has multiple features, okay? That in our case, for simplicity, we say these are all multiple features, all produced on one machine, as an example, okay? Now, the analogous problem is what happens in driverless vehicles or machine vision, right? This is where people looked at semantic segmentation. What are they doing? They're saying, okay, well, you know what? I have a scene image, in this case, this view, and I want to identify all the objects in this image and then be able to label each object per pixel. If I'm using a pixelated representation, which is what 2D images you do. And you say, oh, this is car 1, car 2, car 3, car 4. Okay, I want to identify all the cars and where they are. So per pixel label of object class. Okay, I also identify all the humans in red. Okay, is human 1, human 2. They all belong to the same class. They're all humans. They're in red. But they're each one I identify and label them too, right? That is called semantic segmentation. Okay, semantic means meaning of what that is, object is. So you're ascribing a meaning to each pixel in the image. Okay, according to the class of objects to which that pixel belongs. If that pixel represents a car, it belongs to the car, then that's car. Label for that pixel is car. Now, all the pixels with car of this car will be all adjacent together. That forms the car. Okay, that's what you're doing, labeling. Now, human eye is doing that automatically for you in your brain. You look at it and say, that's a car. You don't say that the air around the car is car. You say the car is that, right? Your human mind is doing that. We want to do something like this for machine parts, let's say. I have a part here like this with multiple grooves and some complex shapes. Obviously, this whole part can be made on a lathe. Okay, I just picked a simple example for you. What this is showing you is if I started with a solid cylinder, which is how I would start on a lathe, and I want to produce this final part, I need to perform multiple operations, right? I need to first reduce the diameter, then I need to do grooving, then I may need to do some chamfering to produce this, which means I'm performing I need multiple operations, each of which removes certain volumes of material. So what is this? This is the total volume of material removed from that starting raw stock that leads to this. Okay? That's what this is. This is sometimes called delta volume. Delta being when you intersect the operation with the stock, what you removed is the delta volume, removed volume, basically. Okay. So semantic segmentation would be that each pixel in this removed volume, total volume that needs to be removed to get this final shape, is labeled that it is either a chamfer or it is a groove or it is whatever, turned. Okay. That is per pixel labeling of the removed volumes tells me how each volume was removed to finally generate this. That is the equivalent problem in semantic segmentation for in the manufacturing context, in this case for machining. Okay? Is that concept clear to you? It still is not saying anything about sequencing. Okay? Yeah. Okay, this is complicated, so I won't go into it. If you're interested in the details of how this is done, go look up at that journal article. Okay, but I will explain conceptually for the benefit of our patient undergraduate students who are here listening and bearing with all of this. So, conceptually, okay, just think conceptually. Don't worry about the details of how it is done. How it's done is in this paper. As I explained to you, I want to produce this. I start with solid volume, raw stock. And what I've done is I've taken this final shape and converted into its voxelized shape. Voxel, the grid-based representation. And then I have subtracted it from the raw stock to identify the total volume that needs to be removed. Okay. Now, I use the total volume to be removed to identify what portion of that total volume is removed by turning, by chamfering, by grooving. In a manner similar to what I was doing before, I have trained 3 models. One is turning, which is basically all turned parts, only it saw unsupervised learning, right? Simply a data set of all turned parts. You have to make sure that they are only turned parts when you trained it. Otherwise, that model will not be a good model. Same way for grooving, same way for chamfering. Now, what do? This is like a windowing process. You know, what do? You scan, right? If I look at this object, there are multiple things. I will say, oh, yeah, you know what? I'm going to scan. This shape is like this here. I'm going to take a window, scan it. And I'm going to change the size of the window so I can recognize. My eyes, of course, are doing this automatically. But if I had to develop an algorithm to do this, it is called panning. I'm panning this object with a window of a certain size so I can recognize the smallest feature that exists and label it as it's turned or whatever, grooved or chamfered. I increase the window size. It's more, and do the same thing. I keep doing this with variable window sizes till I have covered the largest feature size that I can possibly have. Okay, so I go through that type of a operation multiple times, right? Like my eyes are scanning it, except I have to do this serially in this case, or I can parallelize it in a high computing cluster, and I can basically identify, run this removed volumes, the voxels through each of these models and label them, or identify them, which one's the closest feature. Now, I've trained these models, by the way, turning, grooving, and chamfering also on delta volumes, not on the real shapes, okay? Because what I'm inputting is removed volumes only, right? So I do that, I generate what is the closest shape, delta volume that the turning process can produce given this input based on that window size and what the window sees, and grooving and chamfering, and then I finally assign a label. If it's close to what the turning process can do, then it assigned a label as turning, that voxel, same way, okay? And then I combine all the turned voxels, all the chamfered voxels, all the grooved voxels. Now I have identified all those volumes that, according to what operation, can be used to produce them. Conceptually, if you understood that, that's enough, okay? Now we had various data sets. Again, these are synthetic data sets we generated. We call them type 1 cases, type 2, type 3. Type 1 cases look like this, okay? These are some examples only. There were many, many more parts that were used to create a data set, several hundred parts. These are parts where there's a query parts with defined operations. I know which operation is required for each feature in this. Type 2 cases have curved surfaces like this. So these are curvilinear features. And there is no ground truth data. What does ground truth mean? I don't know which operation, okay, ahead of time, okay? And type 3 cases are cases where there are features in these objects. There are many cylindrical rotational features, obviously, but there are also prismatic features that no operation I have can produce. I only have 3 models, one for turning, one for grooving, one for chamfering. Clearly, I can't produce a keyway slot using any one of those. I can't produce some other of these features, drilled or whole features, using those. This is done deliberately because there are unmanufacturable features, unmanufacturable based on those relative to the 3 operations that I modeled, okay, using available operations. I want my model to tell me that these are unmanufacturable. And here's what I can manufacture, here's what I cannot manufacture, right? So these type 3 cases. Now, I'll give you, don't worry about, I'll explain the indicators, the metrics being used here. There's something called intersection over union. That's a common metric that takes what the generative model produced as an output, okay? Intersects it, okay, with the input and then over the union. Okay, now if the object that is produced by the generated model, the generative model is identical to what was input, then this ratio should be 1. The intersection over union should be 1 or close to 1, okay? If it's very different, this will be, close to 0, really, okay? Because intersection between 2 objects that have no similarity will be 0, right? 0 over the union of the 2 is 0. Union is non-zero, obviously. You cannot have infinity, right? You cannot have division by 0. So here is a query part that has been voxelized. Then you determine the delta volume. And what I didn't show you here is from the delta volumes, you can come back and show the actual output, okay? Here is the output. It does a pretty good job, okay? And then it says, okay, what is the difference between output and input? It shows some points here. There is going to be some error, okay? And we use what is called connected component analysis, again, without going into great details, a threshold, if you will, to say that these points that are there, they don't really represent any real feature if they are below a certain number, okay? Which visually you can tell. This is just the fact that you're dealing with data, in this case, even though that's synthetic data, these methods are not, there's some probabilistic aspects to these type of learning methods. So there is some error. But still the IOU, which is intersection over union, okay? Intersection of these 2 divided by the union is close to 1, okay? Is there any unmanufacturable feature? This is UI. This is another metric we defined. What does this represent? This represents whatever is the residual. If this residual is beyond a certain threshold, that means I didn't identify some parts of this object that I can make using any one of my 3 operations. In this case, this is below a threshold because visually also I can see. It doesn't really represent anything. Answer is no. These 2 are covered. Is that a fire alarm? Okay. Okay. Let's look at another example. Here's this object. Remember, these were objects without a ground truth to begin with. I didn't have, I only have turning, grooving, chamfering, right? I didn't have any curved surfaces necessarily. Here is the input and here is the output. Clearly, there are some differences, but it's also pretty close, but there are some differences. As you can see, the IOU is still pretty high, which says that most of these features I can produce. And I have labeled them. What I have not shown you here is the labels, the per pixel or voxel labels. But there is some residual, which is not negligible. You can see it visually as well. So the unmanufacturable feature indicator is yes, there are some unmanufacturable features on this object. Here, there are some features here at the tip that none of my operations can do. Okay, that's what you conclude. Here's the third class. This is the type 3 feature. Clearly, I know, you and I know by looking at it that there are some features here that none of my 3 operations that I modeled can produce. So I should expect an answer that those cannot be produced. So I voxelize it. That's the input. I run it through my model, that window-based process, blah, blah, blah. And it says I can produce this. None of the output is this. There is no slots because it couldn't find a process that can produce those slots. So now you have these 3 slots, which are all equiaxially, angularly spaced, equally angularly spaced. But its IOU is still pretty high because I could produce the rest of the features, but there are some that cannot be produced, which is what I expect. Okay? So that's one example now of using this type of a machine learning semantic segmentation approach on a complex object or more complex object with features, multiple features that require different operations to produce. This is still not saying in what order I should do them. Okay? It's not answering that question, but it's saying I can identify all these operations and some that I don't know what they are. I can't produce them using my machines, is what it says. Okay? That makes sense conceptually? Now, this is basically showing you the labeling, output labels, per voxel labels of the removed volumes, okay? This is showing you that for this object, this is the ground truth. We knew it as object for which I knew ahead of time that these grooves are grooves, those are chamfers, blah, blah, blah. And so this is showing you that what my model predicted, that these removed volumes can be produced by this operation. Indeed, the black ones are grooving, whatever cyan color is chamfering, the green ones are turning. And same thing, turning is here. It's the first you have to turn, then you have to groove, then chamfering or whatever, right? Same thing this is the prediction. The model predicts that this is what it is, so it's very close, okay? And gives you the overall statistics. And if you don't know what precision recall and F1 score are, then don't worry, go read up on it. It relates to the true positives, true negatives, false positives, false negatives, something that tells you what fraction of what is, what fraction of the ones you say are positive are really positive, and so on and so forth, okay? Okay, we have another 15 minutes. I can either skip this last topic and we can talk for another 15 minutes about any of this, or about other aspects of machine learning in manufacturing that I didn't talk about that may be of interest to you based on your research or whatever, or I can cover this. You have an option, and I offer that option to you. The last part is about this supplier selection. It's more about federated learning and so forth. And I already described the problem conceptually to you. Now, how do I select a supplier? But what is key to being able to do that is the types of models I'm talking about here. I just covered that, right? Once I have those type of models that can tell me, oh, here's turning, what I can do, here's what I can do. Then using that, this is now asking the question, well, if supplier 1 can do turning, grooving, and chamfering, supplier 2 can do only turning and grooving, supplier 3 can only do turning, okay? I need to produce this. Who can produce it in some secure way? That's what the problem it answers. But I feel that, the remaining time, it may be better for us to have a discussion, answer questions, ask questions. Is there other aspects of manufacturing that interests you as far as machine learning is concerned? I clearly didn't talk about, time series type of models and other types of things that people do. I feel that may be more valuable, but that's my opinion. I'm happy to cover it if that's what you want. But you also have access to the papers. If that so interests you, you can go read it and send me a question. Okay, if I can't answer it, I'll connect my former PhD student who can answer it. Is that okay with everybody if you have a discussion and stop here in the remaining 14 minutes or so? Yes, no, no opinion? We can discuss. Okay. One vote for discussing. Okay. How many other votes? Yes. He wants to see it. Okay, I'll skim very fast. I already talked about the problem description, okay, of supplying, how do you select the supplier? So the question we are asking is, how do we enable efficient search of suppliers with manufacturing capabilities that match the part design, right? So obviously, if I have access to everyone's successfully produced parts, that's an easy problem to solve. But supplier 1 is not going to tell me what I made. Supplier 2 is not going to tell supplier 1 what they made, etc. Right? Nobody's going to share it. Ideally, it would be great if they shared, but they don't. Okay. What is the idea here? And here now we are not just relying on shape. We are also including material properties, and you can include quality and other metrics as well. So now your data set is richer. It has shape, material properties in this case, and then quality can also be added. The idea here is basically I encode the information for each supplier. Each supplier has their successfully produced parts. Okay? They have theirs. They don't want to share it with me, but they have it. And so they can build their local model, right? They can build a local model, an encoder, decoder model, and essentially have a latent vector representation, a compact representation of what they can produce. Okay? But they won't share their actual CAD models, all of that. They don't have to share it with me. Okay? And they can predict, if given this part, can they produce it? They can answer that question for themselves, right? I also, of course, as the person sitting in cyberspace, want to know what can they make. But I don't have access to their CAD models, right? So how do I answer this problem? So, well, here's the data set. We took publicly available data set as a open source data set. Professor Binal Stali, who was formerly at North Carolina State, they published something. We took it, we added our own, augmented the data set, and we published the data set ourselves. Parts look like this. Okay, this is not the greatest data set. Unfortunately, the diversity of parts is not so great. It has bearings, it has bushings, it has miter gears, shafts, but you see they're all very similar. Some of them are quite similar. From that standpoint, isn't ideal. It'd be nice if there are prismatic parts and all of that. But anyway, this is what we had. This is, again, you said skim. It's very hard to skim without explaining. Otherwise, I'll be just flashing pictures at you. What this is basically we build different types of models. Okay, don't worry too much about it. There are classified type of models that are classified based on recognizing the function of the object. If I input an object, is this a bearing? Is it belong to the bearing class, etc. Okay, is it a miter gear? It belongs to a miter gear. But we built this what is called unsupervised retrieval model. Okay, deep unsupervised retrieval model that basically says, okay, and it's a autoencoder type of a model that basically retrieves the closest matching parts. Okay, retrieves the closest matching parts to the query part. So if I say retrieve 10 parts, it'll retrieve 10 parts that are closest matching. Obviously, you would expect the first one would be the closest matching, most similar. And as you go further down, matching may be less, right? This is what you would expect. This is what this is showing you here. And like you say, for example, with our model here, you input a shaft collar, which is injection molded. So it's a plastic part. This had plastic and metal parts in this case. And from the first object that's retrieved from this latent space, okay, to the 13th part are all classified correctly. They're all shaft collars, okay? They may not be the same shaft collar. These ID numbers represent the actual objects. I have a shaft collar that looks like this, is what this model is telling me, okay? It's similar to your, I say it's similar. This is how similar it is, okay? That's what this is telling you. But if you look at some of these other models, you know, they don't necessarily, you know, it says turning. It identifies shaft collar, yes. The functional class is correctly identified, but the process class is not. It identified as a turned object, okay, not an injection molded object. Whereas the process classifier identifies it correctly, okay. In fact, the first retrieval identifies it correctly. After that, it fails. Bearing, it says something else. So now these are all red ones represent wrong, okay? Wrong retrievals. So this model we built that, you know, at precision of k equals 1, it does a very good job. And I will use this type of a model to train the capabilities of individual suppliers. So let's say I have now 3 suppliers, supplier 1, supplier 2, supplier 3. I use this model to train the capabilities of each supplier using their proprietary data set that they didn't show to anybody, except they have it. So they built that model. This one is building their model. This one's building. All of this is being done simultaneously. And there is a federated encoder model being built, a global model. That global model never sees the proprietary data set. Okay. What it sees, however, are some information is passed. Okay. Some information such as either the weights or the gradients of the weights. The weights are, you know, neural network is nothing but weights and activation functions and arithmetic summation of these, the multiplications of these depends on how many nodes you have, etc. So you basically build simultaneously an encoder model, global model that never sees the actual data, but it sees some representation of that data in terms of weights and gradients or gradients, okay? And by doing so, it learns and then it passes that back. So finally, once you have trained this, I have some latent representation of your capabilities, but I never have access to your data. That's the idea, okay? That's it. And then you can do this, and the rest of the thing is you can show that you can actually identify suppliers with overlapping capabilities. There could be, in reality, two suppliers can make the same things. I should know. You can do that, okay? Now, we are not using any encryption. I say secure, but there's no encryption. You know, you could argue that this is still, somebody can hack into it. Yes, but there are other encryption mechanisms, you know, you can use, okay? Other privacy preserving mechanisms you can use. But the idea is here it's privacy preserving from the standpoint that you don't ask the supplier to share his or her database of parts. They keep it local to themselves. I never see it, okay? Hopefully that gives you an idea, okay? We'll stop here. There are many other things we have done and we are doing. But you see, this is an exciting problem. It's a very difficult problem, or it's a challenging problem. It has always been a challenging problem. People solve it, tried to solve it using kind of reasoning methods or trying to reason. I mean, this is what we are trying to do, is reason. Our human brains can reason so well, but getting a computer to reason is a challenge. And whether expert systems that people use, which are rule-based systems back in the 80s, require you to enumerate all the rules, there's no way. I don't know all the rules. Who knows? Your machinist will have some preferences, okay? She may say, I want to do it this way, and she's able to do it successfully, whereas you may not know that, right? And so we leave it to the machinist to figure out, or manufacturing person. It's embodied in the data, however they did it. That's all I need to know, is what we are arguing. Yes? The UI is this unmanufacturable feature indicator.
So like, can we connect this UI part to the federated model so that if you are not able to manufacture with your capabilities which you have, can we connect them to the
Sure.
and give them the best
Sure.
supplier?
Indeed. You could say, okay, well, this part, this supplier cannot make.
Overall.
Who can make this?
Yeah.
Yeah. Look, you can build layers of complexity on top of that. Yeah. You haven't done it, but you can. We are working on other problems. Multi-tier supplier selection. Those kind of problems. Okay. So, but yes, you can. I think you can. Okay. We have 3 minutes only. See, that was as quickly as I could give you a reasonable overview. What are the questions? I'll stop here. I hopefully have at least have given you an appreciation for the kinds of problems. But as I said at the beginning, there are many other machine learning problems people work on, right? As a defect detection, inspection, etc. Inspection as well, it's always about identifying features and being able to identify features correctly and then being able to classify them. Those are problems that people work on using machine learning methods, different types of, whether it's using 3D CNNs or whatever type of deep learning architecture. I done some work, but I mean, I'm not, that doesn't hold as much excitement for me. A lot of people are doing it. So, but this is not to say that it's not relevant for you, right? I mean, for your work, it may be relevant. So indeed, that type of work exists and people are working. You can find literature on it. The problem of data sets was mentioned. Indeed, one of the limitations is finding good quality data sets to begin with. We had to build these ourselves. And then we are publishing it so others can take it, build on further, which is what the computer scientists did, right? ImageNet, etc. All that led to 3D CNNs and everything else that we have today and take for granted. We need to do the same thing in manufacturing, which we haven't done. Okay, and that's an open issue. And yeah, and it would be great if people can generate these curated data sets and make. And some industries like semiconductor, I believe, I know for a fact that industry is so motivated for defect detection diagnostics that they have generated data sets and provided them, actually. You can find them, actually. They made it open source. They're interested in you showing them how to solve that problem. And then, they'll use it. But in kind of our electromechanical world or mechanical world, we are much more conservative. Manufacturers are. I'll stop there. I'll let you ask me any questions that you might have.
Any questions?
From day one to the last day, fewer and fewer questions. I'm sorry. Maybe it's, but again, it's fine. I presume that some of you, like you, probably are working on machine learning type of things. Is that part of your research? Yes. You're a PhD student? No, master's student. Okay. What about the undergraduates? Yes, please.
question.
Yeah, please.
So in this one, if you vary the dimensions, can the model
Huh.
able to predict
Yeah.
that?
So one of the limitations, of course, you're using a voxelized representation. Some people argue that there are limits to what you can do with voxels because computational complexity goes up. You have to somehow normalize dimensions, so you'll have to do that normalization, would be a way to go about it actually. But even with normalization, the one challenge with voxelized representations, while I think it's a natural representation for 3D objects, in my opinion, computational complexity versus increase in computational complexity relative to resolution, feature resolution, is a challenge. Okay, so the smaller you have objects with very small features and very large features, to capture all of that, you will need much more high resolution representation, and which will slow you down. The training will be very much more difficult, more memory required, etc., to train all of this. We have done some work in that space, like using essentially sparse voxel type of representations, using like octrees, which we've published that one way to address it. But others will argue that, hey, we should use point cloud or we should use B-reps. We're doing some work now on B-reps, but I have my own skepticism of using those type of more complex representations. But anyway, I don't know the answer beyond the fact what I just said. Yeah.
If you don't have any questions, then we will wind up this.
Sir, your work focused more on turning operation, like lathe operations. Is there other works which is being done related to like milling operation or maybe based on other machining operations like EDM or something, and then correlating based on the given product, which machining would be more appropriate?
Yeah.
Because as you mentioned that a key slot cannot be done in a lathe machine, whereas it can be done in a milling machine. If there is a model which can say it can be rather done this way, are there any works going on in this field, sir?
So I want to clarify one thing. I showed you an example where there was lathe and a mill too, injection molded parts, etc. Okay. The idea was not that we would come up with a practical, usable final product, a simulation product, right? Which would require me to consider many, many operations. The idea is to ask the research question, can I use these methods to I use turning as an example, or milling, or turning, milling, and some other operations like injection molding, or casting even, as examples only. And if I can show that I can do this, then you can do that for anything. As long as you give me data.
Yes, sir.
You see? So I need data. And as long as I have data, I should be able to do the same thing, right? So the idea is we are trying to first confirm, can we do it? How well can we do it? If I can do it, then I should be able to do the same thing, provided I have data for these other operations. Okay? The research challenge is not in applying it to other operations, unless those operations present other unique challenges that I cannot solve using these methods. The research challenge is this. If I can do it for 2 or 3 operations, what's stopping me? As long as I have data to do it for 100. No. I mean, yeah, I need more compute power to train and data, all of that. But beyond that, it's not a research challenge. You see, I think it can be done is the answer to your question, right? You can do it, but as long as you have data. Does that help address the question?
Yes, sir.
So we didn't come at it that we will do it for every operation.
Sure, sir.
Yeah.
So my question is, in a practical, if we apply this in a real life area, the supplier, as you told, will not be ready to share all the data set. I mean, all about all the good
Indeed.
parts and everything.
Mm-hmm.
In that case, won't it be a little less effective?
Yeah. Look, if they don't share anything, if they're not even willing to participate in this federated learning exercise, then this doesn't work, right? Doesn't work. So this is an open question. At this point, most people are unwilling to share data. Okay, they will only, if you look at those platform type of on-demand manufacturing websites that are there. Fictive.com, Xometry, you can look them up. They're there. They act as brokers. And the broker in the middle, which is the website person who runs the website, and takes a cut off the supplier. The supplier to the supplier, they have some incentive to participate because they want business, but they don't have enough incentive to give them all the data. They don't give them, right? The way I believe they do this right now is they send challenge parts to them, and they make some challenge. Say, make this part if you want to participate in our network to get business, because we are connecting designers to manufacturers. You make these parts, and there's some random artifact that they design. Based on that, they infer some knowledge about their capability. Okay. So indeed, we need to find ways of. There has to be a value proposition for the companies to share some information, even as little as what I said, right? Don't give me all the CAD models, but give me the weights of your models or something like that, right? But there has to be a value proposition. Let me give you an analogy. You go to Amazon today in India, and you go there and you do a search and you order things, right? Amazon is tracking everything you are ordering. And it presents to you, oh yeah, this person likes all these products, and shows you. Maybe it comes up on your Facebook feed. Maybe it comes up everywhere you go, right? You're freely sharing your preferences. Think about it, right? But you're willing to do that. You're willing to do that. Why? Because they're offering some value to you. So can we think of an equivalent value proposition in manufacturing that we give them? Is there a way to monetize what they're giving that benefits the supplier? That's an open question. How do you do that? You come up with some ideas that will work. That's fantastic. Maybe you could make a lot of money. You could be the next Jeff Bezos or whatever. I'm sure I didn't answer your question satisfactorily, but you get the point. Yeah.
I mean, the answer is
all right.
Any other
Any
question?
other questions? Okay.
Sir, we have seen these examples like for turning, milling, and grooving, and it's perfectly understandable in a process standpoint. But as you mentioned, this can also be used for quality aspects as well, like tolerance. You mentioned it as a separate point.
Yes. Mm-hmm.
I'm just curious, how would that work? Like,
The same way. I mean, so we have done it. I just included here the papers you can look at, but here we added material properties, shape and material properties. So there is actually an encoder for material properties. You can have an encoder for quality, for cost, and for other things.
Yeah,
And you can concatenate, you can do other things. Maybe you can even essentially encode it in a latent space in a manner that there is an association between the shape, the material property, and quality.
I think I can understand these
Yes.
things, but I'm just concerned with tolerances particularly.
Yeah.
Because
Mm.
the suppliers are able to do these processes.
Correct.
But I mean, that data is very complex, right, sir? Actually, I mean,
Well, I mean, depends, right? I mean, do I need the actual raw data, or do I just need to know their ability to achieve what is the tightest tolerance they can achieve, right? And if that's the information, that's probably adequate for me to know that they can achieve this tight tolerance. Looser tolerance is less of an issue. The tighter tolerance are going to be the issue. And if you can use like ISO tolerance specification standards to try and use that representation to encode it, So it's doable. We've done this, yeah. Now, the idea is not to take their 3D CMM data and encode that time series or spatial data. That's not the idea. They can keep that. They have it. But all they would say is, look, they produced a part with these features and this material, and there were some design requirements that specified some tight features with tight tolerances and surface quality, surface finish, and they have to do quality assurance, right? Inspect and say they have met it, and they have to quote numbers and say, okay, they got an RA value of this, or a dimensional tolerance on that feature of this, that meets the requirement. All I need is that data, that I generated this with this part. For this part, this is the tolerance data. I don't need the raw data sets. Does that help answer your question? Okay. Okay, very good. Well, that ends my lectures. It's been a pleasure interacting with you. Hopefully, all of you benefited to some extent, even though some of these things might have been, more than, let's say, past. Maybe you didn't have the background for it, but even if you walked away with an appreciation for the types of problems and possible general approaches to solve these type of problems, then I think I'd feel that I've served a purpose coming here and interacting with you and sharing you. Obviously, some of these things are more cutting edge research problems than approaches that I talked about. But I tried to at least give you a high level understanding of what we are trying to do, right? For the benefit of the undergraduate students anyway. So hopefully, you found it beneficial, and thank you for engaging and asking questions. It's boring for me as a teacher to be here and not have that interaction, because I don't know whether it's making any sense at all or not. I prefer it to be this way, interactive. So I appreciate you interacting with me and asking me questions. I'm sure I didn't answer all of them, but hopefully enough for you to get an appreciation for some of these topics that we discussed. So with that, I wish you the very best in all your educational endeavors or professional endeavors, depending on where you are in the stage of your career. And thank you very much.